Okay, I will start recording. Um, and Today we are going to deal with the stress development. So it's still exercise number 62. And we should keep in mind what we have done up to date and how the design was. And now the question is to analyze the stress in the sensor chip and keep the maximum stress under 75 megapascal. And there is a special solution in the lecture notes, but I would like to derive that solution in a more systematic way. So imagine we have a chip, our chip, and that chip is mounted onto a substrate, and now for simplification we only make a uniform substrate. And what is important, we have an adhesive material, and in the die attachment the following can happen. For instance, when we do the gluing, let's say the whole assembly is stress-free. Then in the gluing process, that glue material, it will harden. Still, we are at that temperature, and then we cool down. And generally we can say what will happen to the stress when we cool down. We have two CTEs of the silicon and the substrate. When we go from the gluing temperature to, let's say, a T ambient, you could say T glue minus T amp is delta T. So that's the cooling. What's the general formula for stress? Due to CTE problems, stress is something like delta alpha times delta T times the effective Young's modulus. Okay. The delta alpha is clear. We already know it, because it's here we can say the alpha of the substrate minus the alpha of the silicon is delta alpha. Okay, that's clear up to now. The problem is the effective Young's modulus. Now let's think about the length of our chip, and that's a relevant length. That length here at the end of the substrate is not relevant. So it's a chip length that we have to take into account. And what will happen when we cool this down? Then we have a little decrease of the size of the chip. Oh, I hate that. And we have a strong decrease of the size of the substrate. Yeah, because the substrate in almost all cases has a higher CTE than the silicon chip, and that would mean the glue would be subject to a shear deformation. So that would be one thing, and that's the case when the glue is hard or when the glue is soft. Can you give me an answer? That way, where we have the shear deformation in the glue, is it for hard glue or for soft glue? Yep. Yep. So that's a situation when we have when we have a harder glue. And in some way we can say, okay, the truth will be somewhere in the middle, so that is for a hard glue. A soft glue could be something like below 1 or 2 gigapascal. A hard glue would be something like 10 gigapascal. So that would be, for instance, a glue which has a high content of filler, and the truth is somewhere in the middle. So in fact, when the hard glue is very hard, so let's say significantly above 10 gigapascal, we could say the material of the glue is not so important, because it just makes a perfect coupling of the chip and the substrate. On the other hand, for the decoupling, what about this thickness of the glue? Does it have an influence or not? In the lecture notes we call it X. Does it have an influence or not? What is your idea? How is shear strain defined? Shear strain if we say that is somehow the length direction, shear strain is just the delta L divided by X. That's the definition of shear strain. And the shear stress, tau, is the shear modulus times delta L divided by X. That is important. That's a basic equation from mechanics, and so it's always important for you to know how shear stresses and shear strains are defined. And in that way we could say, of course, the X could make a difference. So we could say stress when the X goes up, the stress will go down, yeah, because they are inverse. And the stress in the chip is proportional to the shear stress here. The stress will go up when the Young's modulus of the adhesive material will also go up. Now there is an interesting question. What is the influence of the length of chip? What is your idea? When a chip is bigger, do we have a larger stress problem or a smaller stress problem? Yes, when it is larger, the stress problem will become bigger. So normally you could say thermal mechanical stress problem is the larger the part is. And in that way, we could say, okay, here, of course, stress is affected by two factors, and seeing that, we can say, okay, when we just scale the part, make it just bigger by a factor of 2, and also making that adhesive gap larger, possibly there is no increased stress problem. That's the Young's modulus of the glue. On the other hand, the stress influence by the Young's modulus of the substrate, we can say when the substrate is stiffer, normally we will have a problem insofar as also the stress will be higher. Okay, that's the situation, and that's a qualitative influence of the relevant parameters. So we have seen the influence of delta alpha, delta T, and of the of the effective Young's modulus, and that is a function of E glue, E substrate of L and X. There probably are more influences, but in this lecture we just want to see it, let's say, in a semi-quantitative way, and also I would like you to be able to see what are relevant parameters and what not. In fact, now maybe another thing which is interesting, what will happen when the chip is extremely thin? So here we have a chip that is thick, and here we have a case where a chip is thin. On top, where the most important part of the circuit is, do we have what kind of stress do we have here? Can you give me an idea? So here the shape is convex, so what kind of stress do we have here? Yes, we must be correct because it's tensile bending stress. On the other hand, if we would do the same cooling with a very thin chip, what would be the stress here? Do you have an idea? The substrate contracts more than the chip. What will be the consequence for the chip? So it is pressed, yes, and pressed means compressive. So that means in reality, the thickness of the chip, especially in relation to the thickness of the substrate, has a big influence. So, in fact, in between, in cases between very thick and very thin chips, we have a superposition. That is very interesting because we can select a certain thickness of the chip where after the cooling the stress in the chip surface is zero. Yeah, because the tensile bending stress and the uniaxial compressive stress just add up to zero. Okay, that's important for the understanding. So because stresses are not only a result of uniaxial strain differences, but also a result of bending which occurs. In the following formula, which is in the lecture notes, that makes a certain simplification. The formula says the stress, if we have a certain amount of bending, is delta T times delta alpha times the square root of the Young's modulus of the glue times the Young's modulus of the substrate times the length of the chip divided by the thickness of that joint. So in that way we can estimate our stress, and that's also your design task. So now what is important, we must set in our individual parameters. The temperature of the glue you must select. The temperature of the ambient is, let's say, 25 degrees centigrade. The alpha of the silicon is, and the alpha of the substrate is. So here we must have a look what kind of substrate we selected. It's always times 10 to the power of minus 6 per Kelvin times 10 to the power of minus 6 per Kelvin. Then the next question is, what is the L of the chip? What is the X? That's the thickness of the glue. So we take it best in millimeter. Did we forget something? Ah, yes, the Young's moduli. Yeah, And here we have still one thing which is important, that's a prefactor C. The C is a prefactor, so it makes a difference if we have generally hard systems or soft system. So if we have a ceramic and, for instance, a glass solder attachment, then the C is 0.1, and C is 1 otherwise. So one of my PhD students, he checked that formula and you could do it in that way. So now give me the data. What do we take as a CTE for silicon? You take it rounded a little, so it's 3 times 10 to the power of minus 6. For the substrate, we had, in our case, we had a printed wiring board, yeah? Here, for instance, we could take a CTE of something like 12 or 14. Let's say we take 14, could also be 12. And what is the Young's modulus of a printed wiring board? We also have it in the lecture notes. Do you have a proposal? Yeah, in one direction it was 12, in the other 20, or let's say it's also 15 gigapascal. What did we take as a glue? So it's some epoxy filled with something. Maybe a good value for that application could be something like 3 gigapascal or so. We could also take 5 gigapascal. But again, it should be in a reasonable way. So, what is the length of a MEMS chip? Can you give me a value? What is the size of a chip? How many? No, that's too small for gyroscope. Definitely. Here I would rather take 10 millimeter. Yeah, just have a look at the appropriate page where the image is of such a MEMS chip. So 10 millimeter, and what would be a proper thickness of such a glue? Typically that glue is not made too thick. So I would say, for instance, 50 micrometer would be a reasonable approach, because also when you make the glue too thick, for instance, thermal conductivity will be degraded and so on. So now let's proceed. Sigma is 1 times, so the difference is 11 times 10 to the power of minus 6 times, what is the gluing temperature? That is still open. We had made some proposal. Do you have an idea at which temperature could we glue? Yeah, we could do that. In that case, it is often not desirable to go in the application higher. Maybe also we can compute a little easier. Let's say 100 degrees centigrade. Yeah. So otherwise you would have extreme hardening times. Okay, I would accept that. So it's times 75 Kelvin, so the Kelvin is lost. Times, so now we have 5 times 15 gigapascal square times, what else do we need? 10 divided by 50 times 10 to the power of minus 3. So sigma is 750, 825 times 10 to the power of minus 6 times, now we take the square root of 15. What's the square root of 15? It's roughly 4, yes. That's 15, that's 150. Yeah, what is it? Roughly 12. So 0.8 times 12, so, and that is roughly 10 megapascal. So in that way, we have designed a low stress system. The printed wiring board has a low elastic modulus. The glue has a low elastic modulus. That together gives us a value which is under the root. And in our case, the last thing I would like to know, is it tensile or compressive? And so here we must say it is tensile stress we have here, because that is how it will look after the cooling down. So in that way, we have made analysis. That analysis, I must admit, is not very precise, but for you the most important part is to understand how stress is coming into existence, and also to understand what the basic parameters are that have an influence on the type of stress and on the magnitude of that stress. Okay, so for today we were a little faster, and so I would like to stop for today. Do you have questions? Do you think I made a mistake? Stop it. That is 122, you said? So here should be a 2, yes? And that would mean we have 100 megapascal. Oh, that would be too high. In that case, of course, we must adjust a little. Of course, we have several options. We can still go down a little with temperature. So that's a 10, and that's 50 times 10 to the power of minus 3. No, the 5 and the 10, so it's 15 times 10 to the power of minus 3, yes? 15 times 10 to the power of 3, and then, yes, 15, yes. So that would be 100 times, so 15,000. And yeah, again, that is 122, or what you said, roughly, and then we end up. So we have to adjust a little, and so by, for instance, we can decrease that to 3. Maybe we can also go down here a little. Maybe we go down to 12, and we go down here with the temperature a little, as you initially proposed. And then we have a recheck. Also, what we could, of course, increase is also, let's say here, that value. Of course, I do not want to see a millimeter or so, yeah? If you go up to 0.1 millimeter, it's okay. And in that way, we can adjust a little, and then we will come down with a stress. In the exam, please, when you're too high and you change the parameters, then please recalculate it. Yeah, give me the real value. Do not just say I would make the adhesive thicker, but really do it and recalculate it. Yeah, as I said, if you do a chip attachment, you can have maybe up to 0.1 millimeter or so. That's a typical adhesive thickness. If you do the attachment of, let's say, as we had here, that attachment of the printed wiring board on the base plate, or when we have the attachment to the heatsink, then I would say you can go up to values of, let's say, 0.5 millimeter for large area glue interconnections. But for small area interconnections, you typically make relatively thin adhesive layers. Okay, more questions? Yeah, that is a question of the task. In our task here, it was analyze the stress in the sensor chip and keep sigma max under 75 megapascal. Yeah, I made a mistake. I corrected it in the meantime. For some reason, I took the wrong thing. It was the wrong one for the PDF, I think. For the let's say MP4, it should be the correct one. But now I'm going to upload the new things, and so it will be correct after that day. Yeah. Also, what I have prepared this morning, I have proceeded with the lectures. So the lectures are also almost finished. Okay, so see you. Goodbye.